There is a force that controls everything. Not gravity. Gravity holds planets to stars and stars to galaxies, but on the largest scales, gravity is losing. Something else is in charge, something that makes up about 70% of everything that exists, something we cannot see, cannot touch, and cannot explain. We call it dark energy. It is pushing the universe apart, faster and faster, stretching the fabric of space itself. And for nearly 30 years, every measurement we made told us the same story about how this ends. The universe expands forever, the galaxies drift beyond our reach, the stars burn out one by one, and everything fades into an eternal, silent darkness. That was the ending. It was written into our equations. It was, as far as we could tell, inevitable. Then, on a mountaintop in Arizona, a machine with 5,000 robotic eyes began measuring the universe more precisely than anything before it. And it found something that should not be there. The force that rules the universe, the engine of its acceleration, the author of its predicted death, appears to be weakening. If this result holds, it means the most successful model of the cosmos is incomplete. It means the constant that Einstein wrote into his equations more than a century ago may not be a constant at all. And it means the ending of the universe, the one we thought we knew, has quietly been placed back on the table for negotiation. This is the story of how we discovered the universe's fate, and how, in the last 2 years, we may have discovered that we were wrong. To understand why this new result matters so much, we have to go back to the discovery that started it all, because dark energy was never supposed to exist in the first place. In the 1990s, cosmologists thought they were asking a simple question. The universe has been expanding since the Big Bang. That much had been known since Edwin Hubble's observations in the 1920s. Every distant galaxy is rushing away from us, and the farther away it is, the faster it recedes. Space itself is stretching, but the universe is also full of matter, and matter has gravity. Gravity pulls things together, so the expansion everyone assumed must be slowing down, the way a ball thrown into the air slows as Earth's gravity drags on it. The only real question was, how fast is the expansion slowing? Enough for the universe to eventually stop expanding and collapse? Or would it coast outward forever, decelerating but never quite stopping? 2 rival teams of astronomers set out to measure this deceleration. One was the supernova cosmology project, led by Saul Perlmutter. The other was the High Z supernova search team, led by Brian Schmidt, with a young astronomer named Adam Riess doing much of the analysis. Their tool was one of the most violent events in the cosmos, a Type 1a supernova. This particular kind of explosion happens when a white dwarf, the dead core of a sun-like star, steals matter from a companion until it crosses a critical mass and detonates. Because the trigger is always the same critical mass, the explosions are remarkably similar in brightness. They are what astronomers call standard candles. If you know how bright the explosion truly is, and you measure how faint it appears from Earth, you can calculate how far away it is. Measure enough supernovae at enough distances, and you can reconstruct the expansion history of the universe. You can watch the cosmos slow down in real time. Except that is not what they found. In 1998, both teams, competitors using independent data, arrived at the same impossible answer. The distant supernovae were fainter than they should have been. farther away than they should have been. The expansion of the universe was not slowing down, it was speeding up. Let that sink in the way it hit the astronomers themselves. This is like throwing a ball into the air, watching it rise, and then watching it accelerate upward into the sky. It violates every intuition we have about how gravity works. Adam Riess later described checking the results over and over, assuming there was an error in the analysis. Brian Schmidt said his reaction was somewhere between amazement and horror, but the result would not go away. Something was pushing the universe apart, something stronger than the collective gravity of every galaxy, every star, every atom of matter in existence. Within months, the discovery had a name, coined by cosmologist Michael Turner: dark energy. In 2011, Perlmutter, Schmidt, and Riess received the Nobel Prize in Physics. The accelerating universe became one of the most confirmed results in modern science, supported by completely independent lines of evidence. The afterglow of the Big Bang, the clustering of galaxies, the bending of light across the cosmos. The universe was accelerating. That was no longer in doubt. The question was, and still is, why? Here is the strange part. The mathematics needed to describe dark energy had already existed for 80 years. It was sitting in Einstein's equations, unused, like a ghost in the attic of physics. Einstein himself had put it there, and he considered it his greatest mistake. In 1917, Einstein applied his brand new theory of general relativity to the universe as a whole, but his equations kept telling him something he refused to believe. A universe filled with matter could not stand still. Gravity would make it collapse. At the time, everyone, including Einstein, believed the universe was static and eternal. The expansion had not yet been discovered, so Einstein modified his equations. He added a single term, the cosmological constant, written as the Greek letter lambda, representing a kind of energy woven into the fabric of empty space itself. A gentle outward pressure precisely tuned to balance gravity and hold the universe still. Then, in 1929, Hubble showed the universe was not static at all. It was expanding. Einstein's fudge factor was unnecessary. According to the physicist George Gamow, Einstein called the cosmological constant the biggest blunder of his life. For decades, lambda sat in the equations at a value of 0, a historical embarrassment. And then 1998 happened, and physicists realized Einstein's blunder might actually be the answer. A constant energy of empty space pushing outward, that is exactly what could drive an accelerating expansion. The ghost in the attic was real. Here is why empty space can push. In quantum physics, the vacuum is not truly empty. It seethes with fields and fluctuations, particles flickering in and out of existence. Empty space has energy, and in general relativity, energy with negative pressure, tension woven into space itself, produces a gravitational effect that repels rather than attracts. The more space there is, the more total push. As the universe expands, matter thins out and its gravity weakens, but the vacuum's push per cubic meter stays exactly the same. Around 5 or 6 billion years ago, the universe expanded enough that dark energy overtook matter, and the acceleration began. It is an elegant story. There is just one catastrophic problem. When physicists use quantum theory to calculate how much energy empty space should contain, the answer comes out too large. Not by a factor of 10 or 1,000 or 1,000,000. Too large by roughly 120 orders of magnitude. That is a 1 followed by 120 zeros. It has been called the worst theoretical prediction in the history of physics. If the vacuum truly had that much energy, the universe would have ripped itself apart before a single atom could form. So we are left in an absurd position. We can measure dark energy's effects with exquisite precision. We can trace its influence across billions of years. But when we ask our best theories what it is, they miss by a factor so large there is no honest way to visualize it, which raises a possibility that some physicists have quietly considered for decades. Maybe dark energy is not a constant of nature at all. Maybe it is something else, something dynamic, something that changes. For nearly 30 years, there was no evidence for that. Now, there might be. Before we get to the machine in Arizona, you need to understand what was at stake, because the nature of dark energy is not an abstract question. It is the single factor that determines how the universe ends. Cosmologists describe dark energy with a deceptively simple number, the equation of state, written as W. It measures the ratio of dark energy's pressure to its density. You do not need the mathematics. You only need to know that this one number is the dial that selects the fate of everything. If W equals exactly -1, dark energy is a true cosmological constant, unchanging, eternal. And the future is the big freeze. In that future, the acceleration never stops. Distant galaxies cross a horizon beyond which their light can never reach us again, not because they outrun light, but because the space between us stretches faster than light can close the gap. Trillions of years from now, observers in our galaxy would look out and see almost nothing. The evidence of the Big Bang itself stretched beyond detection. The great cosmic story erased from the sky, and then the long dying. Star formation sputters out as gas runs low. In roughly 100 trillion years, the last stars are born. The longest-lived red dwarfs burn for trillions of years more, then fade. Stellar remnants cool into black dwarfs. On timescales so long the numbers lose meaning. Even black holes evaporate into faint radiation. The universe approaches heat death, maximum entropy, no temperature differences, no energy flows. Nothing happens, and nothing ever happens again. Forever. That is the ending if W equals -1. But if WW is even slightly more negative, -1.05 say, dark energy is what physicists call phantom energy. And the future is far more violent. Phantom energy grows stronger as space expands. The acceleration feeds on itself, runaway and unstoppable. In 2003, physicist Robert Caldwell and his colleagues worked out the consequences in a paper bluntly subtitled Phantom Energy and Cosmic Doomsday. They called it the Big Rip. Galaxies are torn apart first, their stars scattered. Then, months before the end, planetary systems are stripped, planets pulled away from their suns. In the final minutes, stars and planets themselves are shredded. And in the last fraction of a second, atoms are ripped open, nuclei dismembered, and the fabric of space-time itself is torn apart. The universe does not fade. It is destroyed. In finite time, on a date you could in principle circle on a calendar. And if W is slightly less negative than -1, or if dark energy weakens over time, a third door opens. The acceleration could ease, stall, perhaps even reverse. And if it reverses, gravity gets its revenge. The expansion turns around, galaxies rush back together, the sky grows hot, and the universe collapses toward a big crunch, a mirror of the Big Bang. Some theorists have long speculated that a crunch could seed a new bang, a cyclic universe, death and rebirth, freeze, rip, crunch. Three utterly different endings, and the choice between them hangs on the behavior of one number. For 25 years, every measurement said the same thing. W equals -1, as precisely as we could measure it. The cosmological constant. The big freeze, case closed. Then we built a machine specifically designed to check. Kitt Peak rises above the Sonoran Desert in southern Arizona, on the lands of the Tohono O'odham Nation. At its summit stands the Nicholas U. Mile Telescope, a 4-meter workhorse built in the early 1970s. For decades, it did respectable, unglamorous astronomy. Nothing about it suggested it would one day challenge our model of the universe. Then it was gutted and rebuilt into something extraordinary. Its new instrument is called DESI, the Dark Energy Spectroscopic Instrument. At its heart is a focal plane carrying 5,000 individual robotic positioners, each one holding a strand of optical fiber thinner than a human hair. Each robot can swivel its fiber to point at a single pre-selected galaxy. 5,000 galaxies at once. Their light travels down the fibers to a bank of spectrographs that split it into a rainbow, revealing each galaxy's redshift. How much the expansion of the universe has stretched its light during the journey to Earth. The redshift tells you, in effect, when in cosmic history that light began its trip. Every 20 minutes or so, the robots dance, thousands of them whirring in unison, re-aiming at a fresh set of targets, night after night. Since 2021, DESI has measured tens of millions of galaxies and quasars, reaching more than 10 billion years into the past. It is the largest three-dimensional map of the universe ever constructed, and it grows every clear night. But a map alone does not measure dark energy. For that, DESI relies on something almost poetic, the frozen sound of the Big Bang. In its first few 100,000 years, the universe was a glowing plasma, a dense, opaque soup of particles and light. Sound waves rippled through this soup, launched by the tug-of-war between gravity and pressure. Then, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. The plasma cleared, and those sound waves froze in place, ripples of slightly higher density locked into the distribution of matter. Galaxies later formed preferentially along those frozen ripples. The result is a subtle statistical pattern in how galaxies cluster. Pairs of galaxies are slightly more likely to be separated by one particular distance, about 500 million light-years in today's universe. Astronomers call this pattern baryon acoustic oscillations. Here is why it matters. That ripple is a ruler, a standard ruler of known length stamped into the sky at every epoch of cosmic history. Measure how large the ruler appears at different distances, and you can reconstruct, step by step, era by era, exactly how fast the universe was expanding at every point in the past 10 billion years. The supernova teams of the 90s had dozens of data points. DESI has millions of galaxies tracing the ruler across cosmic time. It is the difference between glimpsing a landscape through a keyhole and opening the door. In April 2024, the DESI Collaboration, more than 900 scientists, released their first year of results. And buried in the analysis was a whisper of something strange. When DESI's map was combined with the cosmic microwave background and with supernova catalogues, the data showed a preference, a mild one, for dark energy that is not constant, dark energy that evolves. On its own, a hint like that is nothing to lose sleep over. Cosmology has seen countless 2 sigma flukes evaporate with more data. The collaboration itself urged caution. More data would tell. In March 2025, more data arrived. 3 years of observations, roughly 15 million galaxies and quasars. The analysis had nearly tripled in size. The whisper did not fade. It got louder. Here is what the DESI data, combined with other cosmic measurements, now suggests. Dark energy appears to have an equation of state that changes over time. In the Phys, the data prefer a dark energy that was stronger in the cosmic past and is weakening now. The density of dark energy, rather than holding perfectly steady as a true cosmological constant must, seems to have peaked billions of years ago and has been slowly declining ever since. Read that again. The force that dominates the universe, the force whose constancy was the bedrock assumption of modern cosmology, may be running down. How seriously should we take this? In physics, evidence is graded in sigmas, a measure of how unlikely a result is to be a random fluke. 3 sigma is officially interesting, roughly a 1 in 1,000 chance of being statistical noise. 5 sigma is the gold standard for discovery, about 1 in 3.5 million. DESI's second data release, combined with the cosmic microwave background and the largest supernova samples, showed a preference for evolving dark energy at up to about 4.2 sigma. Depending on which supernova catalogue is used, the range runs from roughly 2.8 to 4.2. That is not a discovery, but it is no longer a whisper. It sits in the uncomfortable territory physicists know well, too strong to ignore, too weak to celebrate. And crucially, it is not just one instrument. The preference emerges from the combination of independent probes, DESI's galaxy map, the Big Bang's afterglow measured by the Planck satellite, and 3 separate supernova compilations. Hints pointing in a similar direction have appeared in the analyses of other projects too. No single data set screams. Together, they murmur the same unsettling sentence. The cosmological constant doesn't quite fit anymore. If dark energy is truly weakening, the implications cascade through all of physics. First, dark energy is not the vacuum, not a fixed property of empty space. It would have to be something dynamic, most likely a field filling the universe that changes over cosmic time. Theorists have a name for this family of ideas: quintessence, the 5th essence after the ancient elements. A quintessence field is a bit like a ball rolling slowly down a hill of potential energy. As it rolls, the energy it contributes to the universe changes. Some versions were frozen early on and have begun to thaw, and thawing quintessence is exactly the kind of behavior the DESI data seem to favor. Second, the fate of the universe reopens. A true cosmological constant guarantees the big freeze, but a dynamic field guarantees nothing. If dark energy keeps weakening, the acceleration could taper off. If it fades to 0, expansion coasts. And if the field can go negative, which some models allow, the expansion could one day reverse into collapse. The Big Crunch, dismissed for a quarter century, is quietly back among the possibilities. Some theorists have even used related reasoning to argue the universe could stop expanding surprisingly soon by cosmic standards, within tens of billions of years. Speculative, yes, but no longer unthinkable. Third, And this is the part that excites physicists most. A changing dark energy is a clue. A cosmological constant explains nothing. It is a number bolted onto our equations, with that horrifying 120 orders of magnitude problem attached. But a dynamic field has physics behind it. It can be modelled, tested, connected to fundamental theory. Ironically, some frameworks in string theory find a slowly decaying dark energy easier to accommodate than a perfectly constant one. If dark energy evolves, it may be the first crack in the wall, the first experimental handle on physics beyond our standard models. One number drifting away from -1, that is all it takes to rewrite the ending of everything. Now, before we get carried away, let's give the skeptics the floor. Because extraordinary claims require extraordinary evidence, and the history of cosmology is
Objection 1, it's not 5 sigma.
True. 4.2
anomalies.
sigma at best, and only in certain data combinations. Physics has been burned before. In 2011, an experiment reported neutrinos traveling faster than light at 6 sigma. The culprit turned out to be a loose fiber optic cable. Statistical significance cannot save you from a subtle systematic error. Objection 2. The signal lives in the combination. Strip the analysis down to DESI's galaxy map alone, and the preference for evolving dark energy weakens substantially. The strongest results come only when you stitch together DESI, the cosmic microwave background, and supernovae, datasets from different instruments, with different calibrations and different teams. If any one of them carries a hidden bias, the combination could manufacture a false signal. Notably, some independent reanalyses that swap in different supernova treatments find the evidence softens. The Type 1a supernovae, the very tool that discovered dark energy, are now one of the biggest sources of uncertainty in testing it. Objection 3. Cosmology already has unresolved tensions. The Hubble tension, the stubborn disagreement between the expansion rate measured nearby and the rate inferred from the early universe, has hovered around 5 sigma for years and remains unexplained. Perhaps these anomalies are related. Perhaps both are symptoms of some deeper problem with our model or with our measurements. We simply do not know yet. These are serious objections, and the DESI scientists themselves would echo every one of them. The collaboration has been careful to say the data are consistent with a cosmological constant under some analyses, and that the evolving dark energy preference, while persistent, is not conclusive. But here is why this anomaly is different from most that came before. It did not shrink when the data doubled. Flukes usually dissolve under more statistics. This one sharpened, from a whisper in 2024 to a 4 sigma murmur in 2025. It appears across multiple independent supernova samples, not just one, and the instrument producing it is not a stretched, repurposed experiment. It is the most powerful machine ever built for exactly this question, still taking data every clear night. Either we are watching a systematic error slowly reveal itself, or we are watching, in real time, the standard model of cosmology begin to break. Both possibilities are historic, because the standard model, lambda CDM, the cold, dark matter universe with a cosmological constant, has survived every test thrown at it for 25 years. It predicted the details of the Big Bang's afterglow, the growth of cosmic structure, the abundance of the light elements. It is one of the most successful scientific frameworks ever constructed, And its foundation stone, the lambda, is the thing now trembling. So how do we find out? How do we settle the fate of the universe? We are right now in the middle of the greatest wave of cosmological instrument building in history, and by a fortunate accident of timing, nearly all of it comes online this decade. DESI itself keeps observing. Its full survey will swell to some 50 million galaxies and quasars, and each new analysis will tighten the error bars. If the signal is real, DESI's final dataset should push it toward the 5 sigma threshold. If it is a fluke, more data should grind it back down toward the constant. Above our heads, the European Space Agency's Euclid telescope is surveying billions of galaxies across a third of the sky, measuring not just where galaxies are, but how their shapes are subtly sheared by gravitational lensing, an independent probe of how dark energy shaped the growth of cosmic structure. In the mountains of Chile, the Vera C. Rubin Observatory has begun the legacy survey of space and time, photographing the entire southern sky every few nights with the largest digital camera ever built. Over 10 years, it will detect millions of supernovae, dwarfing every previous catalogue and attacking the supernova calibration problem head-on. And NASA's Nancy Grace Roman Space Telescope will add thousands of exquisitely measured supernovae from space, deep into cosmic history, precisely the epoch where the evolving dark energy models and the cosmological constant disagree most. 4 independent instruments, 4 different techniques, all converging on the same question: is W drifting? Within roughly a decade, we will likely have an answer. Either the cosmological constant survives again and the big freeze remains our forecast, or evolving dark energy is confirmed, lambda CDM falls, and cosmology enters its biggest revolution since 1998, perhaps since Hubble. There are moments in the history of science when an entire worldview pivots on a measurement: the orbit of Mercury, the bending of starlight in 1919, the faint supernovae of 1998. We may be living inside the next one. Step back for a moment and consider what this story really is. A century ago, we did not know other galaxies existed. Then we learned the universe was expanding. Then, within living memory, that the expansion was accelerating, driven by a force we still cannot explain, which outweighs everything we can see by more than 2 to 1. We named it, measured it, built our model of reality around its constancy. And now the universe may be telling us that even that was provisional, that the engine of cosmic acceleration is not a fixed law but a process, something with a history, and perhaps an ending of its own. There is something strangely hopeful in that. The Big Freeze was the bleakest ending physics ever wrote, an eternity of cold, dilute darkness, with no final chapter, just an infinite fade-out. If dark energy is dynamic, that ending is no longer guaranteed. The universe's story may have a different final page. Maybe the expansion gentles into a coast, maybe it turns someday back toward a crunch, and, if some theorists are right, toward another beginning. We do not know, and that is the point. For 25 years we thought we had read the last sentence of the cosmic story. It turns out the sentence is still being written, and, for the first time, we have instruments sensitive enough to watch the ink dry. 5,000 small robots on a mountaintop in Arizona, dancing every 20 minutes in the dark, quietly remeasuring the fate of everything that exists. Whatever they find, a constant or a dying force, we will be the first generation in history to know. The universe is not finished with its story, and neither are we. If you enjoyed this journey, you might like our documentary about the invisible mass pulling our entire galaxy through space at 600 kilometers per second, the Great Attractor. The link is on your screen. Subscribe and join us as we keep asking the biggest questions in the universe.